Okay, so in this video I'm going to talk to you about something called the parametric form of a line, and how lines intersect. And to be honest, the parametric form, that part doesn't take very long. It's a very easy thing. It's the intersection that's going to take time. So just like we did in one of the previous videos, I'm sort of putting these next to one another. In the vector form of a line, we've got a position vector for a point that's on the line, and then we have the directional vector of the line. In the parametric form, all you're doing is you're sort of breaking the thing into its components. You're saying, okay, the x component of this vector will be the x position plus t, and then the x direction. So I'm just writing that in a row. Then I'm taking the y point will be the y initial point plus t times the y component of the direction, and the same with z. So really all you're doing is you're taking this thing and you're breaking it into the x line, the y line, and the z line, and you're writing them as three separate lines. And really not a big deal. I've got an example here where, and you can do this with 2 dimensions also. I decided to do my example up here in 3 dimensions. For this one down here, the thing, so I'm giving you a line in parametric form. I want you to write it in vector form. I think it can help to sort of write them vertically. To write x equals 3 minus 2t, and then y equals 5t, and then z equals 4. And you can even see, or sort of see, I sort of lined this up so that we could see very clearly that if we wrote this as a vector, there will be a point on the line plus time and then the directional vector. The point on the line is all of these things that don't have a t associated with them. So that would be 3, 0, and 4. And then the directional vector is all the things over here that do have a t associated with them. So -2, +5, and there is no t here, which means it's a 0 for the directional vector. So -2, 5, 0. This is the vector form of that parametric line that we just drew. Okay, so converting between the two of them is very easy. The thing that takes a little bit more work is the actual intersection of the lines. And I'm going to do two different parts for this in 2 dimensions and in 3 dimensions. So in 2 dimensions, we find the point of intersection by writing them in the parametric form, and then you're just going to set the x equations equal together and the y equations equal to one another. Doing that will give you 2 equations and 2 unknowns. And when you solve those equations, and this is the important part, when you solve those, that's not the point of intersection, that's the time of the intersection. To find the point of intersection, you plug that time back in, and that'll allow you to sort of check that they intersected, and it'll allow you to find the point of intersection. So I have an example of that below. We'll go through this now. We said that the first step was going to be for us to take this thing and write them in their parametric forms. So that means that x equals -5 plus t, and y equals 13 minus 2t. So that's that line. The other line, I'd like you to pause the video, make sure that you can write that one on your own. You should have x equals -7 minus 3s, and y equals 7 plus s. Now the idea is, if these lines are really going to intersect, then the x coordinates need to be equal to one another, and the y coordinates need to be equal to one another. So I'm going to do just that. I'm going to write -5 plus t is equal to -7 minus 3s, and I'm going to write 13 minus 2t is equal to 7 plus s. Right? Now the idea is I should be able to do an elimination on these two things to solve. And what's really neat about doing them this way is you can actually kind of save yourself some time by noticing these are already in the same order. This is number t equals number s, number t equals number s. If I were to just take this equation, maybe multiply it by 2, and add it, -10 minus 2t equals -14 minus 6s, add these up, I'll end up with 3 equals -7 minus 5s. That means 10 equals -5s, so s is -2. Note, that's not one of the points of intersection. That's one of the times of intersection. What we do now is we take that and we plug it back into the other one to find out what the other time of intersection is. So now I have -5 plus t equals -7 minus 3 times -2. All I'm doing is just taking this value, plugging it into this other equation to bring it down. -5 plus t equals, let's see here, -7 plus 6, that's -1, so t equals 4. So that's the time of intersection for the other line, right? So now we found our times of intersection. How do we actually find the point of intersection? We take this time and plug it into this parametric equation. We take this time and plug it into this parametric equation. Now some of you might be thinking, I could have just plugged it in up here. I'm sure you could, but plugging it into both of them gives us a way to check our answer. Plugging them in is also totally necessary in 3 dimensions. I'm setting you up for that. So I'm going to take this time and plug it into these ones. I'm going to take this time and plug it into these ones just to sort of confirm that this worked. My x-coordinate is supposed to be -5 plus 4. That's -1. My y-coordinate is supposed to be 13 minus 2 times 4. That's 5. So at the moment, it looks like it's going to be -1, 5. We'll confirm on the other side. X equals -7 minus 3 times -2. That's -1. Good, that checks out so far. This is the same as this. Y is 7 plus -2. That's 5. That also checks out. So now that we've done that, we can see that our point of intersection is -1, 5. Okay, there it is. And there's a lot of text here, but in 3 dimensions things change a little bit, right? In 3 dimensions you can find the point of intersection of 2 lines doing the same thing. You write them in parametric form, you set the x and the y and the z equations equal to one another. But in 3 dimensions, you're going to have 3 equations and there are only going to be 2 unknowns. Okay? When you find those unknowns, remember that's not the point of intersection. Same thing, it's the time of intersection. Right? If you want to find the point of intersection, we have to plug those times back into the parametric equations to check them. This right here is where things get interesting. In 3 dimensions, the 2 lines might not intersect. They're called skew lines. You can have 2 lines that are not parallel, but don't touch one another. The easiest way to tell if 2 lines are skew is that the times you find will give you different points when you check them in both lines. Like you're going to think you found the times of intersection, but when you actually check them, you're going to get 2 different points. If you don't get the same point in both checks, they were probably skew lines, that or you made a little mistake. So that's why it's so important that you plug back into both equations. Okay? So I've got 2 examples of that. We'll get to those now. So realistically, the steps here are the same. Right? The first thing we do is we write this in parametric form. X equals -3 plus 2 lambda. Y equals -1 minus lambda. And z equals 0 plus lambda. In other words, just lambda. Okay? You should be able to do the same thing for the other one, so pause the video and make sure that you can do that on your own. You should have x equals 2 plus 1 mu, or just mu. You'll have y equals 0 plus 3 mu, in other words, 3 mu. And you have z equals 2 minus mu. Okay? So now, what happens next? Now, I'm supposed to set these things equal to one another. So I'm supposed to set the x ones equal. That's -3 plus 2 lambda equals 2 plus mu. There is -1 minus lambda equals 3 mu. And there's z equals lambda. I'm sorry, not z equals lambda. There's lambda equals 2 minus mu. And those are my 3 equations. Now note, there are 3 equations and 2 unknowns. What we want to do here is sort of pick 2 of them to work with, right? So I'm going to pick these 2 equations and solve for what lambda and mu are. They seem like nice equations. Plus the lambdas are already lined up. So I'm just going to take this equation and write it underneath this one. I'll put lambda equals 2 minus mu. When I add these up, these cancel. I'll get -1 equals 2 plus 2 mu. So this is going to give me -3 equals 2 mu. So mu is -3 halves. So now I'm supposed to take this value of mu and plug it back into the other one. Lambda equals 2 minus -3 halves. So lambda is 7 halves. So these are my 2 times of the intersection. So what do I do with these things next? I'm supposed to take my lambda and plug it into these equations to find out what the point of intersection is. And I'm supposed to take my mu and plug it into these equations to figure out what the point of intersection is. Okay? So if I sort of start doing that, we'll do them one at a time. First I'll plug 7 halves into the x equation. It would mean that x is supposed to be -3 plus 2 times 7 halves. That means x is -3 plus 7, which is 4. Okay, so great, I found out my x-coordinate is 4. Now, when I plug my mu into this x, I'll get x equals 2 plus negative 3 halves, and that's 1/2. Now this is a problem. These two things were supposed to be equal to one another. I mean, they were supposed to be the same coordinate. So the fact that these are different means one of two things. Either I messed up somewhere and my arithmetic is wrong, or it means that the lines are skew. So at this point, the reality is you check your work, you make sure you haven't made any mistakes. If you haven't made any mistakes, the conclusion that you make is that these lines are skew, right? If there had been an intersection, this would have been the same as this. And the y's would have been the same, and the z's would have been the same. Like, it would have worked out. And that clearly didn't happen here. You know, that's actually another way you could check your work. Plug into y and z. If both of those work, maybe you made a mistake on your x. Like, really, at this point, it comes down to just making sure that you were accurate. So I do have one more example here. It's another one of the exact same problems. If you understood that whole problem, if you know exactly how it works, great, you don't need to watch this one. If you're not sure about that, or if you want to practice it, pause the video, do it on your own, just check to make sure you got the answer right. I'm just going to start walking through this here to see what we get. So first I write them in parametric form. That's -1 plus 2 lambda, y is -6 plus 2 lambda, z equals negative lambda. Over on this side, x equals 7 minus mu, y equals 6 minus 3 mu, and z equals -7 plus 2 mu. Okay. Next, I'm supposed to set the x, y, and z parts equal to one another. So -1 plus 2 lambda equals 7 minus mu. Oops. -6 plus 2 lambda equals 6 minus 3 mu. And the last one, negative lambda equals -7 plus 2 mu. Next step was we sort of pick two of these to work with. I am a fan of the first two because their lambdas are nicely lined up. One of them is +2 lambda and the other is also +2 lambda. So I'll multiply this one by -1 to do the elimination. That's 1 minus 2 lambda equals -7 plus mu. These cancel. I end up with -5 equals -1 minus 2 mu. That means -4 equals -2 mu, and I end up with mu being +2. So that's one of my times of intersection. I'll now plug that in over here. So -1 plus 2 lambda equals 7 minus 2. That means that -1 plus 2 lambda is 5, so 2 lambda is 6, so lambda is 3. So those are my two times of intersection. Now what I'm supposed to do is I'm supposed to go back and I'm supposed to plug this lambda in here, and I'm supposed to plug this mu in to these values. In an effort to save space, I'm just going to take those and do them to the right of there. So when I plug in 3 for that one, I get -1 plus 6, that's 5. When I plug in 2, now I'm going over to the red equations. When I plug in 2 for this x, I end up with 7 minus 2, which is again 5. Those check out, which means I'm good to keep going. Unlike the previous problem where the first two didn't work out and I just stopped because it looked like it was skew, we keep going. So now I'm going to plug in 3 to y, -6 plus 6. This one is 0. Let's find out if the other one's 0. When I plug in mu equals 2 to this one, I get 6 minus 6. That's again 0. This is exciting because these two are now the same. Now for z, again, I'm going to plug in 3 for z. That means this coordinate was -3 with the other one, and this is the exciting conclusion. When I plug in 2, is this going to work? -7 plus 4 is -3. Surprise, surprise, it worked out. It means these lines do intersect. The intersection is at the point 5, 0, -3. And if you've watched this long, I feel like I might as well throw one other piece of information at you. If you asked me, let's say that these two things were like two trains that were traveling on a path, right? So there's an intersection. Does that mean that there's an explosion? Does it mean that there's a horrible train accident? I would argue the answer is no. And the reason is, these two trains both hit this point, but they did it at different times. One train was there at 3 o'clock and one was there at 2 o'clock. So as long as the train isn't like an hour-long train, like a really, really, really long train or a stopped train, it's not a problem. The idea is they were at the same point, but at different times. So in my opinion, there is not a collision here. It just means that the two paths crossed. Okay, so hope that made sense. I know this was another long video. Good luck on the practice problems, and I'll see you in class.